Hello, it's Keith here, and this is lesson 5 of my multi-platform Z80 assembly tutorials. So we're going to be doing some more programming today. We're going to learn some new commands, and the commands today are going to pretty much be all relating to bit operations. Now, we've discussed bytes before, and we know that the Z80 is an 8-bit processor, so our individual bytes are made up of 8 bits. And because the Z80 is an 8-bit processor, it's very powerful, it's very good at working at those bit levels on the 8-bit registers, and we want to try and take advantage of that whenever we can, because that's when the Z80 is going to be fastest and it's going to be most efficient for us. So let's have a look. And what we're going to do today, as usual, we're going to be using WinApe, and we're going to program this assembly to actually work with the screen memory, so that we can actually see the effect of the commands we're running on the screen. I think that's going to be the easiest way for us to see what we're doing. So please have a look at my website when you've finished, because there's the cheat sheet on there which you want to get, and also all of the examples I'm going to give you today are on that website. So if I've gone through them too quickly for you here, then please look at them at your own leisure on the website. So anyway, let's get this out of the way, and we don't need these either. We do need the assembly window. So let's make a start. So as usual, we're going to start at 8000, and we're going to start by loading the address of the start of the screen memory into HL, which is C000. It's of course different on the Spectrum. The MSX screen doesn't work like that at all. So this is an Amstrad CPC only example, and as I've said before, please, even if you're not interested in the Amstrad, just remember I'm only using the Amstrad because it's the quickest way of seeing how those commands work. So let's carry on. And we're going to create a label, and it's called again, because it's where our repeat occurs, and there's going to be different versions of this program, so the E at the end is just to separate it from the other times when I've got a repeat, so the E has no meaning here. And then we're going to load A from the screen. So we're taking data from the screen, we're going to change it and put it back on the screen, and that's how we're going to see what our bit level operations have actually done to the data. And I'll explain it as well, and as I said, the website does show more detail. So first we're going to do a command called XOR. I will explain what that does in a moment. So all of these commands take a byte. I'm using the % symbol so I can specify bits. So all the bits are ones. I hope you know, but if you don't, bits can only be 1 or 0. So 1 is set, and that's what we've got all of the bits set for starters. And then we need to do another load, and as I said, I'm going to put it back into the screen. So this is taking A, putting it back into HL. And then we're going to do a little tricky thing here, because what we want to do is we want to increase HL, and we want to keep doing that until we get to the end of the screen. Now the screen is hexadecimal 4000, 16384 bytes in size, roughly speaking, but there's a slightly faster way that we can do it. IncHL takes 6 ticks of the Z80 processor, but IncL takes only 4. And also, because it's an 8-bit processor, the Z80 can't really compare 16-bit registers. So it's quite hard to, it's a bit of a pain to sort of work out when you've finished the job. So what we're going to do is we're going to split it into 2 parts, because that's slightly faster. So we're going to do IncL, which is the second part, which is the sort of lower part of the address. And then if it's not 0, we're going to go to our loop, to our again E loop here. So I'll just copy that, save my typing. Now, if it is 0, it's time to update H. So we need to do inc H. And then if that's not 0, we go to again. Yeah. Now I'll just explain. The screen goes up to roughly FFFF. So when it increases again over FFF, the HL will roll over to 0. We can't write to 0 because that's the firmware. That will cause a disaster. But we're not doing any harm here. We're taking advantage of that rollover. We're comparing to 0. It'll work great. And as I say, because we're increasing H and L separately, we're working at 8 bits where the Z80 is fast, rather than the 16 bits which we'd be looking at if we did inc HL. So we're saving a little bit of speed here, and when our loop is going to be 16,000 times, any bit of speed is important. So then we do a return. Let's compile that. excuse my monitor here showing everything in the middle of the screen, and we'll just run that. So call and 8000. Now should have done something first, but I'll explain what happened. Now everything just changed colour here, and the reason it's done something slightly odd there is because we're in mode 1. Mode 1 uses 2 bits for each pixel of the screen, but what we're going to do now is we're going to move to mode 2. And mode 2 can only do 2 colours, and that means that there's only 1 bit for each pixel of the screen. So I think we're going to be able to see what the commands we're running today, the effect they have on the bytes that make up the screen, and that way we'll be able to see what those commands are actually doing. So let's give it a go. Call and 8000, and you'll see, hopefully, the screen has inverted. Every pixel on the screen has inverted, and the reason for that is very, very simple. That's what XOR does. XOR inverts a pixel. XOR inverts a bit, sorry. So let's just open my little notepad here. And I'm going to sort of give an example here. So we've got our XOR command, and we'll do our next command. Well, firstly, let me just show you that. So I'm going to change the last 4 bits to zeros of the XOR command. Run it and compile again. And let's just do call and 8000 again. Now you'll see there that if it had inverted the screen entirely, it would have turned exactly the way it started, but it didn't. It only inverted half of each of the 8 pixel character blocks. So let's just clear the screen, and you'll see it's inverted half of each 8 pixel character block. The font's 8 pixels, so you can sort of see when the cursor's moving around. The width of that is 1 byte. Now, if we just call and 8000 again, you'll see these have actually been restored now. They're all back the way they were. Now, let me just explain what actually the XOR command is doing. Let's pretend we have a set of bits in memory, like this. So if A currently contained that, and we did XOR with that, here's how the result is calculated. So each XOR is going to invert, and it only inverts where its mask, which is this here, the value it's got has got a 1 in that column position. So if our default is a 1, if our value is a 1 and we've got a 1, then it will return a 0, because it will apply, because its mask, this bit here, is a 1, it applies the inversion. So that becomes a 0, sorry. That one will become a 1, that one will become a 0, and that one become a 1. But then its mask turns to a 0, so XOR just passes through whatever it was given. So these will stay like they were. Very good. So that's what XOR is doing, and so we can kind of prove that. So let's try some more values. Let's change these 3 bits to 111. Now let's see what happens there. Compile it. And you'll see, I mean, maybe you predicted that, maybe you weren't sure, but what it's done now is it's inverted the first 7 pixels of each 8 pixel character block, because the first 7 bits are 1, so the first 7 bits, effectively the first 7 pixels, are now being inverted. And that's what XOR does. It inverts bits of a byte by the mask you've given it as its parameter. So that's XOR. We'll just run that out because there's some more commands we want to try. So let's try a command called AND. Now, AND is probably a much more familiar term to you, and maybe you can guess what that does. So let's assemble that. Now let's clear our screen and do call and 8000 again. Now, some of the pixels have disappeared. Now, why has that happened? Let's just do a bit more text here. Let's type in some rubbish and call and 8000. And you'll see the right-hand side of each of the letters on the screen have disappeared, and that's because the right 4 bits of each of the bytes of the screen have disappeared. why has that happened? Well, let's just go back to our little notepad again and we'll have a look. So what we've done is this, we've used the same mask, but this time we've done and in the same way as XOR uses its own parameter mask, so does AND. And what AND says is when the value I was given is a 1 and the value the value I was given in A, I mean, and the value in my mask is 1, then I will return a 1. Otherwise, I'm going to return a 0. So in this case here, 1, 1, so it returns a 1. 0, 1, well, it's obviously going to return a 0 though. 1, 1, I'm going to return a 1. 0, 1, going to return a 0. And then you got these 4 bits here, and because this mask is 0, it doesn't matter, it's going to return zeros. So that's what the AND command has done. And as I've said before, all of this is in my is on my website. So if you're not happy with my notepad example here, please just take a look at the website, because I've got all of these examples there and some screenshots as well. So anyway, let's carry on. So that's our AND command, and it's AND is, well, if both are true, if both are 1, by true I mean 1. So let's run that out and let's do another one. So this time we're going to do all. I'll just line that up nicely. And we'll assemble that. And we'll do mode 2 again, just to clear the screen. And call 8000. And what's happened here? Well, at first it might look a bit like the XOR command, but if you look here, it's not inverted the bits. What it's actually done is it's set the bits if they weren't set for the bits which were 1 in the mask. Let me just clear the screen again, and let's put some more text on the screen so you can see it. So as I say, you can see that some of the bits have been wiped out, so they're now always 1, and other the bits have been left alone, and that's because of the way the OR command works with the mask. So let's have another look at our notepad here, and we'll just see. So OR, and I mean, if you think about it logically, it's very sensible. What OR is saying is if the bit in A is 1, or the bit in my mask is 1, then I'll return a 1. Otherwise, I'll just return whatever I was given. So, in this case, well, these are all 1s. So, whatever was in A doesn't matter, because the mask is now 1, so these will all return 1s. But here, well, this is 0. But that's alright, because this is 1, so that returns a 1. This is 0, and this is 0, so that returns a 0. This is 0, but this is a 1, so it returns a 1. And both these are 0. So there we go. That's what the OR command has done, and you can see on screen that that is what it's done. It set those bits where the mask is 1, and left whatever was there before if the mask is 0. And we can just sort of re-clarify that. Let's swap this over, assemble, and we've effectively filled our screen because the 2 commands have filled in opposite halves of the bits. So there we go. Now let's see what we can do next then. I mean, first thing to sort of say is, you know, there's a lot of different bit masks you could do here, so feel free to just play around, you know. Say if you want to type these in, I'd strongly urge it, but if it's too much trouble for you, if you're not that good a typer, just go to my website. You can download the source code, and the source code does have, I'll just show you, the source code does have a lot of extra comments in here. So you know, if I'm not explaining it very well, just please look at the other things I've made available, because hopefully one of those will help you better. So when we're doing a command like OR, what we're effectively doing is setting one of the bits in the original byte. So A here, whatever A is here, once it gets to here, this byte will be set to 1, and these will be left alone. Now the alternative to that is the AND command, which, well, we'll do that differently. Sorry, I'm not doing a very good example there. And the AND command is kind of the opposite. And what it says is whatever these bits are going to be left the same, and this bit is going to be set to 0. So OR is kind of forcing something to 1, and AND is kind of forcing it to 0. And there are some commands that you can do if you only want to change a single bit in a register. There are some commands that you can do that with rather than AND and OR. And what they are is set, and the set uses a bit number and a register, and that is going to be the equivalent of this OR command here. And there's also a reset command, and that's the equivalent of just a moment. That's the equivalent of setting the 7th bit, which is the one to the far right. Now, I should just explain a bit. I find it quite frustrating, but it's a fact, so we have to get over it. But each bit in a byte has a number, and they are numbered from the far right. So if you hear people or websites referring to bit 0, what they mean is the least significant bit, the bit with the lowest value in the byte, which is the one at the far right. And so the 7th bit is the one on the far left, and it doesn't tend to come up in 8-bit computing, but the bits I assume could be numbered further on if you were working in 16 bits. But as I say, it's not a problem for 8-bit computing because 8-bit computer can't work very easily with 16-bit numbers in that way. But as I say, so our set 0 is setting the far most right one to 1. Our reset is setting the far left one, because I've specified 7, to 0. So these commands are identical. I'll just prove that to you. Just a moment. I'll run this out, and we'll just do this. So that's set the bit. Now I'll just do that again. And this time we'll run that out. And that's also set the bit. So our OR command or our set command are identical if the mask just has a single bit in it. So let's try now with the reset command. So if we do paper 1 and pen 0 and do CLS, now we've got a more clear screen to see the effect of this command. And so what we're going to do is do call and 8000, and you'll see one of the bits has disappeared, and it's the far left bit. And then if we just run that out and bring this in, and do that again, we'll call and 8000. Well, you'll see no effect over most of the screen, but you'll just see it changed in the text. And we'll just double check that. So you'll see the command is identical, and you'll think, well, what's the benefit there then? What's the magical benefit of the reset command compared to the AND command? Well, they both use the same amount of memory, they're both the same speed because they use the same amount of memory. But there is one major advantage. The AND command only works on the register A. So if you want to reset a bit in A, you might as well use the AND command, and I tend to because I find it easier to read. But if you want to clear a bit in the register B, you would have to do load A, B and load B, A. Well, that's a lot of commands, a lot of wasted memory and speed. But if you could do, instead you could do reset 7, B. That works just fine. One command doesn't affect your A register either. So if your A register has something important in it, it may not even be an option to do that. So that's a real strong benefit of set and reset when you only need to change one bit in a register, and there are a lot of times you will want to do that. So that's some of the basic commands of working with bits. So let's move on to something a bit more advanced. Now, okay, we did our example. We'll just leave that alone because we're a bit bored of it. So we'll do a new org, and we'll start this time at 8050. And I don't know if you remember, if you saw last week's lesson, we were looking at how to pass parameters from BASIC to assembly language, and we were reading them in with the indirect register IX, and we're going to do that again. So if you've missed that, I'll try and explain it to you, so hopefully you understand it, but please go back and have a look at that, because the IX register is very important, and if you're going to work in BASIC, then how to pass parameters, BASIC on the CPC, sorry, then you definitely want to know that, because it's a really powerful tool for when you're getting started, because it allows you to use BASIC to help you limit the amount you need to do in assembly. So anyway, So we're going to do CP1, and that's because we know that BASIC passes the number of parameters it was given in the accumulator. And then if we weren't given one, we're going to return. So if we've got this far, then we were obviously given one. So we're going to load B with IX plus 1. So we get the most significant byte of the 16-bit parameter that was passed into B. And then next, we're going to load C with IX plus 0 to get the least significant bit. And then we're going to load HL with and C00. So the screen memory again. So it sounds pretty similar, of course. And we'll just copy this over. You can probably guess at this point the order I wrote these test programs in because of the changing labels and the changing memory addresses. But okay. And so again, we're loading in A, and we're going to use the command bit 7, B. Now, you just mentioned set and res for set and reset, and I didn't mention bit, and I didn't mention it because I knew we were coming to it here. What bit is, it's like a compare command. So in the same way as we could have done CP, and then our we could have done here something like CP % 1 0 0 0 0 0 0 0, like that. We could have done that compare command, but we can also do bit 7, A. These two commands are identical, and again, it allows us to compare to other registers, bits in other registers other than the accumulator, because CP always works with the accumulator, which is very limiting. And if you look at this example, we're going to do a jump if the bit is 0 to no AND. And we couldn't do this with the accumulator with the CP command because the accumulator's got this important data here we don't want to get rid of. So that's why using this bit command is really powerful for us. And what we're going to do here is AND C. And then here we're going to do a no AND label. And then we're going to do bit 6, B. And then we're going to do jump if it's 0 to no OR. We'll cover what this means in a moment. Let's have a look. So no OR, here we go. And then we want to have here OR C. And then here we just need to have all of this once again. So you see, all of these programs are very similar. The basic core of the program is just to get data onto the screen so you can see it. But I'm using it to describe these different functions and to maybe teach you a few programming concepts along the way. So if we go to assemble, no errors, that's good. So if we just do call and 8050. Now we need to know what kind of parameter to give this program, and so I'll just tell you there's two parameters it will take, and they're both part of the same 16-bit register. So the highest byte is always going to be 80 or 40, and this tells the code whether to use an AND command or an OR command. So we'll do a 40 first, and then the second part is a bit mask in hexadecimal format. So for example, if I just bring my calculator into here and set it to binary, so if we wanted to do 11111100, I think that's 8, and then so we'll use FC. Okay, I apologize, my copy pasting has got ahead of me. I have forgotten to put the command in that actually puts the data back onto the screen. Very silly of me. Let's try again. And let's run that program again, and maybe we'll see a result this time. So what it's done is, maybe you recognize that, it's ORed the bytes on the screen with the bit mask of FC, and the reason it's done that is because 40 goes into here with our B, which is used with these comparisons to see what bits are set, and 40 in hexadecimal is actually the sixth bit is set, and so this OR command gets run, and then the data is written to the screen. If we do a CLS and we do call and 8050, 80, because we remember we did 40 last time, and then we do our FC. You saw there some of the bits disappeared. Not very many, but some did. Let's do another one called 8050, comma, and 80, and let's just do 05 this time, 05. And you see almost all the bits disappeared because we're using an AND command. So we've kind of split that 16-bit value into two halves. One half is now the parameter saying use an AND or use an OR, and the second half is the mask. And we've used the bit command to compare, to see which of those bits are set and which aren't, for to make our decision of which command to use. So that's just a little example there of using the bit command to do a comparison with one of the bits in a byte, and how to use a byte, how to use different bits in a byte for different decision-making procedures, because this can become quite useful when you're writing your games and things. In the ChibiAkumas game I've written, a single byte is used for every kind of movement within the game, and different bits have different, some of the bits will decide how fast to move up, some will decide how fast to move left. One bit might decide, oh well, this is a special command, and the other bits have other meanings. So by splitting a byte into individual bits, it gives you more functionality for very little memory, and it also allows you to program in clever ways, because you can slice different bits up and branch off to subroutines, and then come back and then use other bits and branch off again, so that that one byte can make lots and lots of decisions for you. So something definitely worth considering there. So that's our second example, but there's lots more unusual bit commands that we need to look at, unfortunately, and they are quite complex. So let's have a look at them. So we need another program, unfortunately, so let's make a start. So org and 8100, and then again LD HL, comma, and C000. Very boring. Again B, yeah. So I'm using different label names each time, because although they're almost exactly the same program, you can't use the same label, and the example file you download from the website has all of them contained together. So by using different label names, they don't conflict with each other. So of course, you're welcome to use whatever label names you want to, if you're following this at home. So there's a lot of different options here. I'm going to be lazy. I'm just going to paste them in. Sorry. So there we go. So we're going to use a command called SRL. And as it says just next to it what the command does, there's no prizes for guessing. Fill the screen with some junk. Did you see something happen? Maybe you didn't. So let's make it a bit more clear. Oh, trying to use the copy command. That's a very silly thing of me to do, because some of the bits have vanished, so the copy command can't understand what it was trying to copy. So I've written a little program here. All it's going to do is it's going to run that our assembly command, and then it's going to run the rerun the basic program. So it makes it an infinite loop, and we can just stop the loop at any time by pressing the escape key twice. So we'll run, and you'll see all of the bits shifted to the right. Well, let's just have another look at that. If you remember that each of these letters is a single byte in width, maybe you can see what happens. So the bits are kind of shifting to the right, and they're disappearing. Well, why is that? Well, let's have a look what the SRL command says it does. It shifts the bits to the right, and it sets the top bit, the leftmost bit, to 0. And that's what happened. All of the pixels of the letter kind of shifted to the right, and the left-hand side got blanker and blanker. So that's what that command does. But we've got all of these other interesting options, so let's try those as well. So that's a bit strange. Well, what's that? Well, as it says, shifts it to the right, but it keeps the top bit the same. Why would you want that? You probably think that's quite strange. Well, it's simple. If you think about negative numbers in assembly language, all of the bits are kind of inverted. So if you wanted, one of the powerful things about shifting the bits to the left and the right is it effectively halves and doubles numbers. And when we looked at mathematics before, we realized there's really no multiplication division commands in assembly language, and that's only partially true. There's no commands for any kind of multiplication and division, but if you're only doubling and halving numbers, then actually you can just shift all the bits to the left or to the right, and that will have the effect. If you don't believe me, if you're not sure on that, please have a look at my other video where I used a assembly language. Well, sorry, I used a basic calculator that worked in binary and hexadecimal, and I showed that quite clearly. But you can take my word for it. If you double a number, you're effectively shifting all of its bits to the left. If you halve a number, you're effectively shifting all of its bits to the right. So that's a great way of doing your mathematics very quickly. And if you're game programming, I would categorically recommend you always work in doubling and halving when you need to do multiplication and division. The ChibiAkumas game effectively has no multiplication or division in loops, with the exception of when it's looking up addresses and it knows it needs to allocate 6 bytes for each index in the sprite files and things. That's the only time there's any multiplication. It's actually done by repeated addition commands. And there's no loops involved because loops are slow. So, as I say, if your game logic needs something to double in speed, to increase in speed, sorry, always double. If you need to increase again, quadruple, octuple, whatever, halve, quarter, eighth, always work in halves and doubles, because that's the thing that the 8-bit processor is fast at. So anyway, that's why we've got a weird command like that. But we do have some more interesting commands. So we're going to use RRC, and we'll just type some junk on the screen so you got something to look at, and do call 8100, and we'll just run our program and we'll see. And you can see there that the bits are actually kind of floating around the byte and coming back around in a big loop. Well, that's quite curious. It looks nice on the screen at least, but there's a quite useful function for this. Let's suppose you have a let's just go to my notepad here. Let's suppose you have a number that's going to go from 0 to 3, like this. And then suppose you're going to use it as a memory lookup or something, and you actually need those 2 bits all the way over here. So your 0 to 3 becomes a 64 to 192. Well, how are you going to do that? Well, it's very easy. You just use this shift command, shift one of them over there, shift the other one over there, and you're done. Just 2 commands, and you've converted a very small number into a very big number instantly. It's really good, and I do that a lot, and everyone doing fast as 8-bit programming will do it a lot because it's really good. Now the next command, you'll see here if you're reading ahead, uses something called the carry. So that's going to be a bit tricky for us. So let's have a go, and do call . And you'll see that the bits are kind of shifting across the screen here gradually. So you're probably thinking, well, it's just moving everything along. But you've got to understand, unfortunately, how it works, and it's a bit of a pain. Now, I don't know if you remember when we're doing our comparisons and saying if something's smaller, we've got this C and this NC thing. And that the C in there is actually the carry bit. And what a carry bit is probably best explained if I just create another little program. So we'll do another one here at 9,000. Sorry, talking and typing doesn't go well. So we're going to do one here at 9,000. And I'll just get my example here. So we're going to load A with 192, and then we're going to add 128. Okay? And we're going to return. So we'll put a breakpoint here. Now, A is, of course, our accumulator is, of course, an 8-bit register, and an 8-bit register can only go from 0 to 255. And because it's already 192, we got a serious problem when we add 128 to it. And if you followed my my hexadecimal tutorial, you know it's going to go round in a circle and start back at 0. But it also does something else. So let's have a look. So we assemble that. So we'll call 9,000. and we'll have a look here. So if you look here, there's a C here, and that's the carry flag. So it's currently 0, which is good. So we'll just step in, and we'll see that this has now been loaded to C0, which is 192 in hexadecimal. And then we're going to add 80, which is 128 in hexadecimal. And it's become 40, which is 64 in hexadecimal, because we've filled up the 8-bit register and rolled around. But what you also want to look at is the carry here has now switched to 1. And why has it done that? Well, let's have a look. I will just bring in the website here because I spent a lot of time writing this, so I'm not going to type it again. So what the carry effectively is if you're doing 8-bit mathematics, and in some cases even 16-bit mathematics, the carry flag is the bit that is the kind of, it's the 9th bit in an 8-bit register or the 17th bit in a 16-bit register pair. So when two mathematical calculations overflow the 8-bit register, like in this case, the carry is the extra bit that needs to go somewhere else, and it's kind of up to you. You can either ignore it, or you can then add that to another register to make two 8-bit registers into one 16-bit register, two 16-bit registers into one 32-bit register, or you can save it to memory and create a 128-bit register or something if you want. So as I say, it's kind of the overflow that allows you to use 8-bit registers for more than they can cope with on their own. And now, in the case of this screen routine, what's actually happening is one of the bits is getting pushed out of the byte into the carry, and then when the next byte is processed, the bit in the carry is pulled out and pushed into that one, which is why it has this cycling scroll through thing. Now in theory, one of the bits, the first bit we process, which would be the top corner of the screen, must have got some junk from whatever was in the carry beforehand, but you can't see it because it's insignificant. It's probably 0 anyway, but it did happen. Now in the same way as when we just looked at using rotation, which moves the bits around a single byte register, the carry allows us to take individual bits out of a register and put them into another register. And this can be used by repeatedly rotating right with carry and then rotating left with carry. We can move bits out of one register in one order and push them into another register in another order. I know that sounds slightly tricky, but you can do it. So just bear that in mind, because there may be times you need to do that. As I say, we're playing around with the screen here, and it's just to give you a visual representation of what the commands do. It's not really that practical an example, and it does only work in mode 1 this cleanly. I will explain a bit about mode 2. It does only work in mode 2 cleanly. I will explain a bit in mode 1 later, but mode 2 is the sort of easiest for us to see this. So we've just had a look at those. So let's have a look at another program then. Now we've all looked at her moving to the right here, which is all very well and good, but there are the same commands for rotating to the left. But unfortunately our example needs to be reprogrammed, because if we're going to move to the left, we have to work from the end of the screen to the start, because moving from the start of the screen to the end will be overwriting the data in the wrong order, and some of the commands, like the carry command, won't work in the same clean way. So let's have a go with this one then. So we'll just I'll just cheat again, and I will paste in the 4 commands here. And we need to do another label, and we need to load A from HL again. And unless I'm going to make the same mistake, we need to do HL into A. There we go. Then dec L as usual. And we need to do, this time we need to load A with H, because we've got to do a more complex comparison. We can't compare to 0 because we're going the wrong way round. So we're going to compare to BF. I'll explain that in a moment. And if we aren't at BF, we're going to do JPNZ, comma again C, and then we're going to return. There we go. I forgot a command there. That's never good. So let's see that in a loop and just see what that does. So let's reset to mode 2 and we'll run that program. Now it's not very clear, so we'll run it again. But if you watch the letters, you'll see they kind of slide to the left and everything fills in yellow because that's what bit 1 does. And you'll see our command it does say shift to the left and sets the bottom bit to 1. So that's kind of doing what we expected it to. Now I did say I'd explain, so let's have a look at the commands. So we're starting HL at F00. Now that's a bit odd, you might think. Why aren't we starting at FF? Well, the reason I've done that is because we're using a non-zero here. And we're using a dec L there. So when L is 0, which it is because we've set it to 0 here, and we do the dec, it ends up as FF 255. So this non-zero is not true. If I set this to FF, you would end up missing the byte FF00, and the only alternative would be to do a comparison here, and that would mean LD A, L CP FF, and that's going to waste a lot of extra processing power because this is our really heavy loop. We've done it here, but here is less important. This is only run 255 times. No, this is only run 64 times. This is run 255 times. So we need to make this as efficient as possible to get the overall efficiency good. So and then we're doing decrease commands here. So we're starting from F and going down the screen memory. And if you remember, the screen memory it starts at C000. And so when we go below that, we end up at BF00. So that's why we're doing our comparison to BF here. And when we don't, until we get that far, we keep repeating. When we do get that far, we finish. So that's what SLL does. So let's have a look at SLA. Well, exactly the same, only it sets the bottom bit to 0. So there we go. And you can see there's another one here, which you can probably guess because it says it's on screen, and because as we've already seen the other one, it's going to wrap the letters around. So if we run it, they go round and round in circles. And again, that can be used for converting a very high number into a very small number. And then finally, we've got rotate left with the carry, which in the same way as last time, is going to kind of do a scroll, and it's going to the left. Now I should point out that when something goes off the left-hand side of the screen, it's actually coming back the line above on the right-hand side of the screen. And so this isn't enough to do. If you're thinking, oh great, I can use this to make a scrolling routine, it's not enough. You'll also notice it's horribly slow, which is why games scroll so badly on the Amstrad CPC. But that's another subject. So now, one thing to just explain, I'm not using the fastest commands I could here. I'm using RLA, and there's a space here, but I can actually take that space out and do RLA here and RLC as just one command. What's the difference? Well, RLA with a space can be used on lots of different registers, so there's an RLB and RLC and things like that, whereas RLA is all one command. It's a smaller command, it's a single byte command, so it's faster, but it can only work with the accumulator A. So I've used the sort of more crude versions here, the less efficient versions here, just so you can see the commands that will work with other registers. And then when it comes to you need to actually do the fastest option when you're doing your own code, you can look at what options are available to you, and you should decide to use RLA if it's only the accumulator you need to do it on. Now, I did say I'd explain about mode 1, so let's have a look at mode 1. And let's do the wrap command, because maybe that's going to help us understand mode 1 a little bit. So mode 1 uses 2 bits for each screen pixel. And if we just do our run here and see the command running, you'll see something quite odd there. It's not just shifting to the left, it's actually changing colour in the process. And you may think, well, what on earth is it doing that for? Well, it's simple. The way the memory is laid out on the Amstrad CPC in screen mode 1 is not necessarily what you might expect it to be, or at least it's not what I expected it to be. So how does the Amstrad CPC screen mode work then? Well, it's quite simple. Let me explain it to you. If you think of a 4-pixel cluster of the screen as a single byte, which is the way the mode works, the bits in it are split into sort of 2 sections. The first 4 bits will define color 1. So if the first 4 bits are 1, then all of that byte, all those 4 pixels, will be in color 1. If the second 4 bits are 1, then it will be in color 2. And if all of the bits are 1, those 4 pixels will be in color 3. And of course, if none of them are 1, then it will be color 0, which is the background color. Now, you should remember that on the Amstrad, it's very easy to test this kind of hypothesis just by using a poke command. So if we do poke and C000, and then we put in a byte like this, we can see how that byte will look on the screen. And you can see here that the first 4 pixels of the screen have now turned to color 1. So if we change that, and we just change this to OF, you'll see that those 4 pixels have now changed to color 2. And I've just scrolled the screen, which will make it confusing. And if we change it to FF, you'll see they've changed to color 3, which is red. And then if we change it to 00, you'll see they've disappeared because they're now color 0. So as I say, screen mode 1 uses a cluster of 4 bits to define each pixel, and those sort of clusters come together to define the colors. It's a bit strange, I know, but I think the reason for it is because it makes rendering the fonts, which are stored in the firmware at 1-bit color depth, easier, because it allows the firmware to sort of copy those bits into a byte in a single color, and then to shift those bits around to change the color. So it does make sense from that point of view, but it's a bit strange from other points of view, and it's not the way that the memory works on the MSX, and it's not the way I expected the memory to work. But as I say, if you are confused, make these little programs and just try it out. Do the poke command and see what the bytes you're expecting to draw actually end up looking like on screen, to just confirm whether it's working how you thought it was. So there we go. Now let's have a look at our last program. So we're done with playing with bits for now, but there is another important thing we can discuss here, because one of our earlier programs had a rather significant limitation to it, and it's this program here. Now this program, if you remember, loaded in some parameters from our user, and then it actually did an operation on screen depending on what parameter the user had specified. Now that's very good, but the problem with it is you've got these conditions here that say, well, what's this bit set to? And if it's set to this certain value, jump over this, and then the same again here. And the problem with that is that anything in this sort of central point is going to be run 16,000 times during the screen fill command. Now that's a big problem, because our poor old Z80 doesn't have a lot of processing power. It can't afford to be wasting processing power on conditions like that in such a heavy loop. So really what we would like to do in an ideal world is to have a way of not needing a condition inside that loop. And you may think, well, that's going to be impossible. We need a condition. We're using the best command there is. You can't do it. But it's not true. And there's a reason it's not true. Now, let's just look at what happens when we assemble our program. Now, you maybe you've understood it, but what happens to your commands is they are converted to bytes, and those bytes are stored in memory. And when we run a program, whatever our computer assembler is running is also in memory. Everything's in RAM, and we can change RAM. What does that mean? Well, what it means is we can make a program reprogram itself so that a part of the program can be switched to do a different thing each time you run it. And that means we can take our condition out of the loop, we can put it before the loop, and we can get that condition to reprogram part of the loop, so the loop has no conditions, no jump statements. It only does the one command again. Sounds a bit crazy, doesn't it? But let's have a look, because it's a tricky concept and it can lead to mistakes, but it's a very powerful concept, so let's have a look at it. So this is going to be our last program. and it's going to be and 8300. And we're going to again take one parameter, so we'll compare to 1, and if we haven't got it, we'll return. There we go. So we're going to load A from ix plus 1, and again that's the most significant byte of the parameter, the 16-bit parameter we're passed. And what we're going to do now, I'm just going to paste these in. These come at the bottom, but we'll put them in now for clarity. So here we've got some commands, and these commands are never actually going to be executed. What they're here for is the assembler is going to compile them and store them as bytes in memory, and we're going to use this as a bit of a shortcut to work out what bytes these commands compile to, so that we can modify the code with those bytes. Just bear with me, as I say, I know this is confusing, but it's a great example. It's the exact time you want to do this kind of thing. So we'll load HL with SM and. SM stands for self-modifying, in case you were wondering. And we're going to compare to 1. And if we've got a 1, we're going to do a jump to the start. So why are we doing this? Well, command 1 is going to be our AND command. So we set HL to our AND, and if we've got it, we start up. But if we haven't, we're going to load HL with SM OR and compare to 1. And if we've got it, we're going to jump to the start. And then finally, compared to 2, sorry. And then finally, we're going to do SM XOR compared to 3 and jump to the start. So if you think about the execution here, it's going to load HL with AND, and then if it's got a 1, jump to the start, otherwise with OR, and then jump to the start, otherwise XOR, and then jump to the start. And then the start is going to be here, and what we're going to do is we're going to load A from whatever value of HL we've got, which by the time we get here is going to be one of these commands. And what we're going to do, and it's going to be the command that was specified by the high byte of the parameter that was passed. So we're now going to be loading the byte that makes up the AND command, the OR command, or the XOR command. And then what we're going to do is we're going to load, and we've not written it yet, but we're going to load self-modify with A. And then after that, we're going to do another load A command, and this time we're going to load it from IX plus 0, which is the least significant byte, which will be the rightmost byte in the 16-bit pair. And we're going to then load that into self-modify plus 1. Bear with me, we will have a look at self-modify, the label we've not defined yet, and we'll understand why what we're doing here. And then we're back to our normal code. So load HL, and C000, and again D. I've got a lot of these agains in this program. So load A from a HL as usual, and then here is our self-modify label, and we've got just 2 no ops. Now what does no op mean? Well, no op does absolutely nothing, and its byte value is 0. So why have we done that? Well, our self-modify commands here are going to load a byte into self-modify, which will go here, and then another byte into self-modify plus 1 here. And so these commands here will swap one of these commands here and the second parameter that the user passed, which we loaded from here, and it's going to load that second command into here. So these 2 bytes will disappear, and we'll prove that by putting a breakpoint. And we'll actually put a breakpoint here as well, just so we can see before and after. So there's our self-modify command, and then here, rather than before where we had conditions and jumps and slow nasty things like that, we're actually done. So all we do is load HL with A, and then inc L, and then jump NZ, again D, and then inc H, and then jump NZ again D, and then return. And then let's assemble it. And I've made a mistake. It was a stupid thing to do, wasn't it? forgot my LD command. Yeah. So we need to switch to mode 2 here, and then if we just compile our program and do call and 8300, comma and 01 for command 1, and then our bit mask, which we're going to try as F0. And you'll see here we've got our two no up commands here, which are the label self-modify. You see that there? And we're about to load in the command A from the address HL, which is 8335, and it's going to load in this here, which is E6, which is the byte command for and we can have a look at that. And what you want to do if you're ever doing self-modifying code is check out that cheat sheet that's available on my website, because you'll see on it you've got all of the assembly commands and the bytes that make up them. So the one that we're using here is the and n command, which is E6 with n. And n, of course, is whatever value you're using, which in the template command is 1. So E6 is the byte equivalent of the AND command. So if we just carry on here, let's just step through. Now it currently says AND 0. That's because we haven't loaded in the second byte from the parameter. But now we have loaded in the second byte from the parameter to F0. So now you'll see that the two no-up commands have now been replaced with an AND F0 command. And that will do the task that we've defined. So we'll just take out that breakpoint, or we'll never finish. And you'll see the bytes have disappeared, which is what you would expect from an AND mask. So we'll do 8300 again. And this time we'll do 02. And we'll do F0. And if we look at our source code, 2 is an OR command. So this time it's loading HL from 8337, which is the OR command, and it's going to load in an F6, which is the byte equivalent of an OR. So let's just step in, and you can see the OR command is now in the code, and it's filled in with an OR. And we'll just do mode 2 again, and we'll just put some junk on the screen so you can see. And then we'll do our last command, and 8300, comma, and 03F0. And if we step in, we can see it's now an XOR command, which again is what we'd expect. So it inverts the screen. And there you go. What we've done there is we've created a loop, a very intensive loop that repeats a lot, which we can change the function of without any conditions within that loop, and that is very, very powerful. One thing I should point out is I wouldn't actually recommend doing it in the way I've done here. There's a template here, and then I'm reading in from that template here. It's quite wasteful. Firstly, you've got the bytes that are here, and also you're loading in 2 byte values here for the addresses where the command is only 1 byte in itself. So what if it was real code that I was doing and not an example, I would have actually looked up in the cheat sheet what the bytes really are, and then I would have loaded like with the AND example, as I said, the AND example E6, I would have actually loaded H with AND E6, and then I would have then done here load A, comma H, and load self-modified. That would have saved a few bytes, and it would have been a little bit faster, and then I would have had no need for this, so I could have just deleted this altogether. So that's definitely what you would want to do in a real example, but this is a complex sort of thing. You'll still get a massive efficiency boost from this example. If doing it this way, if this is what you're comfortable with, is perfect. But if you really want to get every byte out of the system, every ounce of performance out of the system, you would want to skip these sort of template commands and do it directly. Now, I know self-modifying code looks very, very daunting. I know it's confusing, and it can make your programs hard to debug. All of those things are true. So you're probably thinking, well, this is a beginner's tutorial. Why are you teaching me this? Don't be ridiculous. I thought all of those things when I started assembly language programming. But the truth of the matter is, with Z80 programming, or with 8-bit programming even, self-modifying code is the way you make your program faster than everyone else. It's the way you make the 8-bit processor do the things that the 8-bit processor shouldn't be able to do. So in the early days, just forget about it. Just think that's a hard thing. I'm not going to bother with it. I'll just ignore it. Great, do that. It's the right thing to do. But one day you're going to be looking at your code thinking, oh, it just needs to be faster. Oh, there's got to be a way of doing this. And that's when the self-modifying code will come in for you. And by that point, you'll probably be feeling more confident with the general stuff. So I wanted to take this example because this is the exact example to use self-modifying code. So I wanted to show you it today, but as I say, I understand it's probably too much for you. So just remember it exists and come back to it at a later stage. So we've covered everything we needed to today. I hope you've enjoyed it. I hope you found this interesting. There's plenty more stuff I'm going to teach you, so please come back for the next lesson. And I hope you enjoy it. Please check out my website, download the cheat sheet, download the examples. If you don't want to type these programs in, then you can download the sources file, and the examples are pre-entered for you, so you can just tweak them and run them. And as I said before, if you look at the sources, they do have detailed comments in them, so if you want to see in more detail, and as well the website itself, if you go to my website, you'll see there is a description of all of the commands as well. So if you don't feel this video has explained things as well as it could, just please look at those other resources and hopefully it'll help you out. Thanks for watching today. Please subscribe if you want to see more. Thanks a lot. Goodbye.